Welcome everyone. This is our 110th live stream geometry. We have two other people here with me today. And today I am taking 3 problems from a Facebook group that I've gone on a lot recently. So the Romantics of Geometry Facebook group. And I am taking another 3 from the European Mathematical Cup. So if you'd like to join us in the future, feel free to email me at mgreenbeat01@gmail.com. We meet every Sunday at 8 a.m. U.S. Central Time. All right, so I will share my screen. Hold on just a moment. All right. So here's the first problem. So we have a triangle ABC with circumcenter O and orthocenter H. All right. Maybe move this down a little bit, and M is the midpoint of BC. All right, so let's draw the circumcircle and the circumcenter O. M is the midpoint of BC. U is the intersection of BC. So we want to draw the tangent at A to the circle. All right. Sorry. Here's the tangent at A. Let me just move this up a little bit. And this will be U. Then we draw the orthocenter H. And we draw the circumcircle BHC. And that is the reflection of the circumcircle of ABC over BC. So that's kind of well known. We pick a point P on it. Let's see. What if I make this point P right there? We could call it this point P, for example. And we let BP and CP intersect the sides. At Y and Z. And we draw the circumcircle of PYZ. And actually, in the Facebook group, the first part of the problem is to show that AZPY is cyclic. But that's not too hard, so I'll prove that. But the main part is we want to show that the perpendicular, basically UQ is perpendicular to AM. So that is the main problem. So I'll make this look better. See, it's the diagram's a little confusing because UA is not tangent to this circle, it's just tangent to the big circle. So I'll try to draw that better. So if I draw really, I think it's going to be a little tricky to see no matter what, I feel like. But just remember that UA is not tangent to the small circle, it's just tangent to the big circle. So the reason why it's easy to see that AZPY is cyclic, so angle ZPY is angle BPC, which is angle BHC. And the reflection of H over BC lies on the circle. So that would be like BH prime C, which would be 180 minus angle A. So that's why this is cyclic. Let's see. Let me draw it. This almost looks like it passes through Z. I think that's a good picture. And I'll be right back, just a second. All right, I am back.
UQ is the radical axis of A and BHC.
It's the radical axis of
Point circle A and BHC.
Okay, so BHC and the
Point circle.
What?
Point circle A.
Oh, the point circle. Okay. All right. So interesting.
Q
Well,
lies on the axis. Clearly.
okay. So you yeah, has the same power with respect to both, and then Q oh, these circles are tangent, basically. Is that why? Like, how do we know that the power of Q with respect to this circle is Q? Well, wait a second.
QA equals QP.
QA equals QP.
This basically implies because Q lies on the perpendicular bisector of AP, right?
Q lies on the perpendicular bisector of AP. Yeah, so QA equals QP. Okay, and then U. So basically, have you solved the problem? So basically, I see that U has the same power with respect to the big circle and this circle and point A, right?
Yeah.
But for the point Q, is it obvious? I'm just trying to think. So
Is QP
what?
QP is tangent or something? UP.
Oh, UP is tangent?
To the circle BHC.
Let's see. I'm not sure if that's true. No, that's not true.
Oh, okay.
Hey, Stefan, thanks for joining.
Hello.
So yeah, I see that U lies on the radical axis of the point circle A and circle BPC and the circumcircle ABC. So it has the same power with respect to all three, but point Q, I'm trying to think how to use that.
Is circle AZPY tangent to ABC?
I don't think so, no.
Then how would you say that U lies on that the radical axis? It is like the radical center of those three.
So it's not this circle, it's the point circle A, and then this circle, and then this circle.
Oh,
Yeah.
okay. But that doesn't really have a connection with point P in itself.
Yeah, that's the thing. So yeah. All right. So we could try drawing like the foot of the altitude from A. So maybe I'll draw both these 2 points. And if the problem was true, then we'd have a cyclic quadrilateral, right? So this would be the orthocenter. I don't know if this helps, but I'm just checking. All right, I'm going to delete that. But yeah, so I mentioned in the beginning, it's actually the first part of the problem online on this Facebook group was to show that AZPY is cyclic, but that's kind of trivial by an angle chase, because angle ZPY is BPC is BHC is BEC, which is 180 minus CAY.
I think that there was some lemma about these points Y and Z.
Oh yeah.
But I don't know exactly what. I think it had some connections with media.
Interesting. Kind of like that diagram. So AU, AB, AC, and the submedian are in harmonic conjugation. So maybe that helps. Are these Are these concurrent? Yeah, it looks like they are. So is that
Yeah,
obvious?
maybe that was it.
Okay.
That concurrency. That is the Humpty point. So it kind of makes sense.
Okay. So basically, yeah, you're saying this is a right angle. Is that obvious that yeah, is it obvious that those concur? I guess it's yeah, it doesn't seem that obvious to me that those concur.
No, it can be angle traced. I just did it.
Oh, really?
If you intersect the median with the circle, HBC, again,
Okay.
then you would make a parallelogram that is well known and not hard to prove. Not that circle, the circle HBC.
Oh. Okay, so I have to shrink it, sorry.
Yeah.
Oops, sorry. Just a tiny bit. There we go.
Yeah, so here ABGC is a parallelogram.
Okay.
That is well known. So we can just do an angle chase to show that angles AYP and AFP are equal. That would be like this. So angle AYP, that is equal to PBC plus ACB.
Okay.
And ACB is just GBC since we have a parallelogram.
Okay.
So angle AYP, that is equal to GBP. You just add PBC and GBC, and that would
We
be.
can just use that since AC is parallel to BG because they're a parallelogram. AYB is YBG, right?
Yeah, you can do that.
Okay.
Okay.
Sorry.
And that is just equal to AFP. See, if you intersect, you define F as the intersection of AM and HBC. And that's how it goes.
F is the intersection of like these, and then it's just an angle chase.
Yeah.
So then AFP. So AYP equals YPG, which is PBG, which is PFA. And so then you show this is cyclic. Makes sense? All right.
Well, now we just need to show that UA is equal to UF.
Okay.
Since we have that the perpendicular from U to AM is just perpendicular from U to AF.
Yeah, it makes sense. It's just by symmetry, right?
And now we just don't need point P at all.
Okay.
And this is like well known, I think.
Okay. So, because yeah, F is independent of P. So yeah, I could hide everything. But let's see. UA equals UF. Let's see if we can try to prove it.
I've seen that before. I think the quickest proof or something like that. I didn't think of that proof. I had something different, but it uses some radical axis with points as circles.
Oh yeah, UF has to be tangent to the circle, and that's probably an angle chase, right?
Maybe. Maybe it can invert or something like that.
Because UA squared is UB times UC. And if UA equals UF, then that would mean UF squared would be UB times UC, so that would have to be tangent. And that's probably an angle chase, right?
Maybe. Also, one interesting thing is that if we reflect F over BC, then we will just get the symedian point on the circle.
Okay.
That is well known.
Yes.
And yeah, this just finishes. Since it is a symedian, then UF prime is tangent to the circle.
Because ABF prime C is harmonic.
Yeah.
Well,
And
yeah.
then by reflection, you just have that. Yeah, you just have that. UF is equal to UF prime, and that solves it.
So UF prime is tangent. That makes sense. All right, so I will type it up. All right. So let G be the reflection of A over M. Or yeah, so we didn't define this, or let AM intersect BHP. So actually, first I'll show APYZ is cyclic. But yeah, I'll define G first. So let AM intersect BHPC at G. It's well known that ABGC is a parallelogram. So then, okay, first I'm going to show that AZPY is cyclic. So angle YPZ equals angle BPC BHC, which is BEC. Maybe minus angle A. That means that AYPZ is cyclic. And then let AM intersect BPHC at F. F. Then it's well known that that's like the Humpty point, right? So, but first we'll do the angle chase you mentioned. So angle AYB. Let's see. So we're going to show FYs on this circle because angle AYP is YPG. YPG. Or I could just say PBG, which is PFA. PBG and then PFA. And then that means that, what is it? AYFPZ is cyclic. And then once we know that, so A, B, F prime, C is harmonic. So let F prime be the reflection of F over BC. It's just a well-known fact that this is harmonic, A, B, F prime, C. Is that, so basically, like, how do you know UF prime is tangent to the circle? Oh, I guess it's just well known that that's a symmedian. So So yeah, so then this is harmonic, okay, so AF prime is a symmedian. So ABF prime C is harmonic. And that means that UF prime is tangent to, it's like Chuan is rejoining or joining on a different device. BHC, and then reflecting over BC, then UF prime is tangent to, this would be tangent to ABC, so reflecting over BC, then we have UF. Oh, whoops, UF prime is tangent to ABC, and then UF is tangent to BHC. And this means UF squared equals, or UF equals, yeah, I'll just write it all out. UF squared equals UF prime squared equals UB. Well, actually, I could just say equals UA. Yeah, UF equals UF prime equals UA. That's UA. And that implies that UQ is perpendicular to AF, which is AM. Whoops. And then I'll move on to the next problem. Just a second. So, well, we really should show that F is the Humpty point, right? But I guess it's well known that the AM intersects the circle BHC at the Humpty point, because it's well known that that's cyclic quad. So, yes. So I'll just say by video 5, I think, on my channel, F is the Humpty point. All right. And then implies UQ is perpendicular to AF. So UQ is perpendicular. Yeah. All right. Sounds good. So we will move on to the next one. So there was one problem from someone from Vietnam. This one looks like it might be a little tricky. So let's try it. How do I maximize? There we go. So we have a triangle ABC. So this problem involves the mixed linear end circle. And Abdul Heel told me today I was having some trouble with the desktop GeoGebra, but I just realized you can make tools on the internet version by creating tools here. So I'm going to try that out next time. So let I be the end center. So let's draw our end circle. And if we drew that, let's draw the mixed linear. We only need the mixed, well, we do need the whole circle, not just let's do that. Whoops. Let me close this. We need that, and we need this. And we need this. So this will be the center of the circle. And there we go. So let's draw midpoint of arc BC. That might be useful. Let's hide the whole line, just draw the segment. And X is the touch point. And then we draw the perpendicular to AX at X. And it meets this at A prime. And then we draw A prime. And it meets the circle at X prime. And then we draw the circumcenter of XA X prime. And that is supposed to give us its median. Whoops, this should just be X prime here, not HX prime. So N is the center. That. Let's move the diagram up a little bit. And call this N. We want to show AN is a median of ABC. Hide this. Okay. So, is there anything special? We could try drawing the midpoint of arc ABC, just see if that helps. I'm going to call it M. And these are collinear, just well known. I'm not even going to draw this for now. What's special about point N? Is NX tangent to both circles? It looks like it. I'm not sure if that's easy to prove, but it appears, is that just an angle chase that NX is tangent? And maybe NX prime is also tangent. It sure looks like it. So let's think about that. Well, if NX is tangent, then by symmetry, NX prime should also be tangent. And it's probably easier to show NX prime as tangent, I would think. wonder, so N lies on the perpendicular bisector of AX. Does M also lie on it? No.
Can you prove that nx and nx prime are tangents?
I haven't proven it.
Okay, let's say we have that. Then we would need to show just that x prime, bc, and tangent at a concur.
Okay.
That would be equivalent to showing that n is on the C-median.
Is that because it would show that those rays are harmonic, like AB, AC, AN, and that?
I think it can be proven easily by some polars.
Okay. So if we showed that they are concurrent, then bipoles and polars, that would show that AN is a C-median. Okay, so let me try something. All right. We don't know they concur, but let's see how we can show it.
Oh, you can angle chase that nx and nx prime are tangents.
That NX and NX prime are tangent.
Yeah. You have that nx is equal to nx prime. Actually, define n as the let n be just as it is.
Okay.
Angle nx x prime, that is equal to 90 minus half of x and x prime.
X and X prime. Yeah. Okay.
And x and x prime, that is twice x a prime a.
Okay.
So basically nx x prime, that angle is 90 minus angle x a prime a.
Okay.
And since we have that angle at x is 90, then this angle is x a prime.
A prime. Okay. So which is, so that would mean it has to be tangent.
Yeah.
Okay. So by an angle chase, we can show both these are tangent.
Yeah.
And
So
then,
the other one is the harder part then.
okay. And then once we show that, I think the problem's solved, right? Because then H lies on the polar of N, so N lies on the polar of H. And so basically ABJC is harmonic and AN is a median, right?
Yeah, but we have to show the concurrency.
Oh yeah, we have to show the concurrency.
And if you noticed, we didn't really use the full problem for showing just the tangents. I basically just used that A prime is 90 degrees.
Yeah, I was gonna say, there wasn't a lot of information you had to use to show that these are tangent.
So that other information is used to prove the concurrency then.
Yeah. Interesting. All right, looks like we have another person joining. Hey Pascal, thanks for joining us. Good to see you. So this is our second problem. And we've kind of reduced it to a simpler problem. So yeah, you have a triangle, you draw the mixed linear in circle, it touches at point X, then you draw the perpendicular at X and it meets the circle again at A prime, and then A prime meets the big circle at X, and then N is the circumcenter of X, A prime X, and we want to show that AN is the median. So that's the problem, and we've reduced it to showing that the tangent at A, BC, and XX prime are concurrent. What if we take these three circles and try to use the radical axis theorem? So this circle, the circumcircle of ABC, and the point circle A. Then we want to show that BC is the radical axis of the, I don't know if that's actually true. I don't think it is. No. The point circle A and this circle.
Well, it must be true, right?
I think the radical axis would have to pass through H, but I don't think it would have to be the line BC, right?
Yeah. But what if it really is line BC?
It could be. Let's check. So N is the center of it.
So
I don't think it is line
and
BC, because if it was line BC, then BC should be perpendicular to AN.
Yeah. So it isn't.
So then, that we can figure out, that means that the radical axis is the perpendicular from H to AN. Whoops, sorry. That's perpendicular bisector. So this is the radical axis. But yeah, I'm not sure how helpful that is. I wonder if it passes through the center of this circle. It does. Interesting. So the center of ABC is tangent. Oh, well, actually that's kind of obvious. So yeah. Because since these are tangent, then the power of O with respect to the circle is OX prime squared, and the power of O with respect to that is OA squared, so they have this, it has the same power. So it lies, so yeah, HO is perpendicular to AN. There's probably other ways to prove that too. Oh, so yeah, I don't think we need any of these points down here. Really, we could just show that the tangent at A, B, C, and the perpendicular from O to the median are concurrent. This feels a little well known. Like, isn't this is this like the A dumpty point? Is K like the A dumpty point? We just need to show O, K, and H are collinear.
No, that doesn't make sense.
Doesn't make sense.
Isn't equivalent. It's like if you assume that hx and x prime are collinear.
But here's what I'm thinking. So basically, I'm gonna start out, but like I'm still gonna try to use so by the radical axis theorem, but by the radical axis theorem, these are concurrent. So the point circle A, the circumcircle of ABC, and this circle.
Okay.
So we know that OH is the radical axis of the point circle A in this circle, because O has the same power with respect to both, because OA squared equals OX prime squared. And also we could say the same with H. Because HA squared is like
hx times hx prime.
right. So if we use the radical axis theory, so we know that these three concur, right?
Yeah.
And then if we could show H lies on BC, that would solve the problem. So basically, then we could get rid of this and all this, and we could reduce the problem to showing that just like these concur. If that makes sense. So and K is the.
But that is also then just equivalent to showing that AN is the median. So it's like if you're going in circles.
Oh yeah. It is kind of like going in circles. Yeah, you're right.
So I had a different idea, which kind of looks good. So if we intersect AX with the mixed linear in circle again,
Okay.
then we would just have like one trivial collinearity.
Okay.
That is A prime, F, and K, just because we have 90-degree angle.
Okay.
And also F is the midpoint of A prime K. So if we project through A onto ABC, then K goes to X, F goes to G, and A prime goes to X prime. And we also need this the parallel through A to KF. However, that is just line AO. You can see that by a homomorph which takes in circle to the circumcircle. So we can kind of define X prime as this point which makes this harmonic bundle X G X prime L.
So, well, the definition of F is the center of that circle, but it would happen that that's all true, right? So you project A through those, so X, G, X prime L is harmonic. Yes.
Yeah.
And so N, G, and L are collinear.
Yeah, that is also true.
And H, J, let's see, X, G, X prime L. so we know AXJ X prime is harmonic. So yeah, HJ is tangent circle.
No,
No.
we don't know that. We don't know that HJ is tangent.
But we know that NX and NX prime are tangent, right? To the
Yeah.
So that means AXJ X prime is harmonic.
Yeah.
So then that proves that HJ is tangent, right?
No, since we don't know the concurrency.
Oh.
Look,
Yeah.
I don't think that it is good at all to do anything with N anymore.
Yeah.
It would be best to just hide it and try to do it with other points. Like N is useless.
So hide point N.
Yeah, I would do that.
Okay. So okay, so you're just saying to show that these are concurrent. Okay, so like you said, so you're projecting these 3 points through A. So XGX prime L is harmonic, right?
Yeah.
Right.
So we need to prove that X prime collinear.
Yeah.
We can show that the angle HAX is equal to the angle H prime A, because the angle the angle X prime A is equal to the angle XLA, and HAX plus XAL is 90, and so is XLA plus XAL is 90. So we can conclude that X prime collinear.
Okay, so you're showing that X prime A equals H X prime A?
Oh, wait.
Say that one more time.
Oh, I think I missed something.
Okay.
Yeah, you made a mistake. You basically said that those three are collinear in that proof, because you said that AX prime X, that is equal to wait. I'm not sure, but I think that you made a mistake. Yeah.
Yeah, I did make a mistake.
It's all right.
So one thing that may be useful here is that GX and ED are concurrent on BC, concurrent BC.
Okay.
That is well known.
All right. And is PK tangent to that circle? Let's see. Looks like it. Although it's kind of hard to tell, actually. Maybe not. No, it's not.
Maybe we should try to do root BC inversion.
Okay.
Everything looks kind of nice when inverting.
Okay, so we're inverting about radius squared of AB times AC, and then followed by. Do you want to reflect it too, like the
Yeah, yeah.
reflection about? Yeah.
So L goes to the foot of perpendicular from A to BC.
Okay.
Okay, G goes to the intersection of AG and BC.
AJ and BC.
What is J?
Oh, AG and BC.
Yeah, yeah.
Awesome. Okay.
Okay, X goes to the touch point of the X circle with BC.
Okay. All right. I'm gonna reflect S over T. Sorry, X prime goes to S.
No, X goes to S prime.
X goes to S prime.
Yeah, and X prime is the only point which is not ideal.
Yeah.
But we can work with it since we have a harmonic bundle. And the last one is H. H goes to the point on the circle, which makes a trapezoid.
So the H being the orthocenter.
No,
This
H
H.
is
This H.
yeah, that H. So you take the line through A perpendicular to BC and
Right.
intersect it with circle.
And H goes to U.
Yeah. So we want to show that H, X, and X prime are collinear.
Mm-hmm.
So we would need to show that A, U, S prime, and the image of X prime are cyclic.
Okay.
So we can basically just intersect the circle AUS prime with BC. Okay, it is yes.
Yeah,
I didn't know that.
interesting.
Actually, that is obvious.
It's obvious,
when
yeah.
you intersect. Yeah.
So we
So
have,
basically, we need to show that QS, R, and S prime are harmonic, and this looks familiar. I've seen that before.
so wait,
For
we
sure.
have to show, yeah, I think that's obvious. You just take parallel lines through those 4 points to AQ, and it goes to AR, the in center, and the X center, which are, it's well known those are harmonic.
Oh yeah, yeah. So
but-
that's it.
How do we know that X prime goes to S?
Since inversion preserves cross ratio,
Okay.
and we have those are harmonic, and we have those two pairs of harmonics, QSR S prime and XG X prime L. That's why we know that X prime goes to S.
Okay, so XG X prime L is harmonic.
That's what we
by-
showed earlier.
It's what we showed earlier. You project through F, right?
Yeah.
Interesting.
Also, one interesting thing is that then X prime is actually the tangency point of the mixed linear X circle. So the one which touches ABC externally.
Really?
Yeah.
I did not know that. It's the X prime is the X mixed linear touch point for
It is a mixed linear touch point, but mixed linear X circle this
X
time, not the
circle
in
instead of
circle.
the N circle.
Yeah.
That's cool.
I mean, I didn't know that until we discovered point S.
Interesting. Okay, so what did we project? Oh, we projected A across KF A prime. Okay, that's how we got that. That was harmonic. Okay, this is a really good solution. All right, so I'm going to write it up. Hold on just a second. Okay, so, and then we hit a lot of stuff too. So I'm going to delete. Let me think about how I want to do this. I'm going to delete that point P, and I'm going to rename a few things. So I think that's all we need. Delete. Okay, so first we're going to show that these concur. And then once we show they concur, then it's kind of obvious AN is a symmedian, because then basically we have a harmonic quadrilateral, right? Because then that would mean that AXG X prime is harmonic. Wait, is that right? I'm getting confused. No, that would mean so once we know these concur, I'm trying to remember what I did. Anyways, first I'll start out by showing those concur at H. So consider a square root of BC inversion followed by reflection over AI. I'll just say label the points as shown. Now label the points as shown isn't that obvious, because like some of them could probably, it's not clear how which way they're defined, but I'll just say that for now. So consider a square root of BC inversion followed. Well, we want phi to be the composition of the two. So phi of h equals u. And then, let's see, phi of so I'm trying to remember what was mapped. So phi of L is Q, right? And what other points did we want?
G goes to R.
G goes to R. Oh, I forgot to close this. So those all get,
Yeah, and X to S prime.
and X goes to S prime. And we know that that's well known. For the last one is well known. And so then we're going to show, so F is the midpoint of AK prime. And so then we project through A onto the circle. But we first need to know that AL is parallel to K prime, and that's obvious by homothency. So by homothency at X, projecting through actually, I'll flip these. Projecting onto the circle. Equal to K A prime F infinity. Which is equal to X G X prime L. And since that's harmonic, so thus the images of these 4 points are also in harmonic conjugate. So the images of those 4 points are harmonic. So implies, okay, so that means that Q, so X goes to S prime. So S prime, S prime R, phi of X prime and Q. Okay. But yeah, by projecting onto line AI, or by taking parallels through line AI, or I'll say parallels to what do I call it? AQ. Then we have S prime R, S prime R, SQ. Equals, that would be IA and intersecting with line AI. And we have, this would be IA, and then R goes to just R, and then S goes to I, and then that goes to A, Q goes to A. Where IA is the AX center. A center. And then, so that means that phi of X prime equals S. S. That looks a little weird, so I'll fix it. And then since AUSS prime is cyclic, that means X prime, and H are linear. So let's make some room here. So AUSS prime is a cyclic isosceles trapezoid. That means that H, X, and X prime are collinear. Okay. And then now to finish off, we did some stuff with point N too. So we showed by an angle chase that NX and NX prime are tangent. And once we know that, and then H lies on the polar N, so N lies on the polar of H. And thus AN is a symmedian. That should solve it. So, all right, so we have angle N. What was it? Angle N X A prime. And I'm just trying to remember that angle chase that you mentioned at the beginning. So X A prime. So this angle we found in terms of this angle, which we then found in terms of this angle, which we then calculate in terms of that angle. So okay, so angle nxx prime is 90 minus angle x and x prime over 2, which is 90 minus that would be 180 minus angle x8 prime x prime. And then from there, it's probably easy to see that that is just angle XAA prime. So this implies that nx prime, nx and nx prime are both tangent to ABC. And that means that n lies on the polar of H. And that means that H lies on the polar of N. And then H lies on the polar, or the other way. Yeah, we flip these statements. So H, N, and H. And that means that AN is a symmedian, or, oh, I made them all H. What am I doing here? So H lies on the polar of N, and which means that N lies on the polar of H, which means that AN is a symmedian. All right, that was a good problem. So let's just make a little bit more room down here so people on YouTube can see the final results. Not too much room here, but oh well. That should be good enough. All right, thanks a lot for the solution. That was fun. Let's move on to the third problem. Oh, this one looks really interesting, actually. I don't know if it's really easy or it's hard to tell.